welcome. I'm Caroline Keeson. I work for Tip of the Mitt Watershed Council. I'm excited to be working with the City of Sheboygan to bring this workshop to bring awareness of green infrastructure to the city. And we're happy to have a grant from the Great Lakes Commission's Emerging Green Champions mini grant program. So I'm going to introduce our presenters. We have Don Carpenter, who is the Vice President of Drummond Carpenter, LLC, and the Professor of Practice at Lawrence Technological University. We also have Erik Petrovskis from Meijer Incorporated. He's the Director of Environmental Compliance and Sustainability. And then we also have Claire Schwartz, who is a civil engineer, senior civil engineer at Fishbeck, and she's also the mentor for this program. So we're happy to have everybody today. And I'm going to turn my video off to get started with these polls. Okay. So we're going to do a little quiz game at the beginning just to get everyone thinking. So if you are calling in, I'll be reading out the questions so that you can just think about them. And then during Don's presentation, he'll actually give us the answers. Okay, so the first one is green infrastructure uses plants and soil media to reduce stormwater runoff and improve water quality, make gray infrastructure obsolete, store the volume of water from a 100-year flood, or all of the above. Oh, for some reason, you're just viewing the... Let me relaunch that. Okay, let's try that again. Okay, now you should be able to vote. There we go. Okay, so most people said green infrastructure uses plants and soil media to reduce stormwater runoff and improve water quality, or was it all of the above? So we'll wait to see what Don says. Okay, the next one. Oops. Let's see. Okay, the best way to protect the stability of a stream channel is to control the peak release rate from large storms, control the volume of runoff from small storms, control the volume of runoff during large flood events, or mimic natural hydrology of the watershed. All right, and the winner of this poll was mimic natural hydrology of the watershed, with a few answers for control the volume of runoff during large flood events. Okay, next one. Okay, so this one's about impervious, or what inhibits the infiltration of stormwater into the soil and increases runoff. So impervious surfaces, compaction of soil during construction, applying salt to the roadway, or both impervious surfaces and applying salt to the roadway, or all of the above. So all of those things inhibit infiltration of stormwater. Okay, so the most common answer for that one was D, which is impervious surfaces and applying salt to the roadway. Okay, this is an easy one. Green infrastructure and green stormwater infrastructure are the same thing. True or false? Okay, so most answers said false. So we'll see if Don can clear that up for us. Okay, designing with green infrastructure always results in standing water. True or false? Okay, everybody said false for that one. Let's hope we're right. Another easy one. Green infrastructure does not work in cold climates. True or false? Okay, and everyone hopefully said false because we live in northern Michigan. Okay, this hard surface can allow rainwater to penetrate into the ground. Concrete pavers, asphalt, concrete, or all of the above. Okay, so most answers were concrete pavers with one answer each for asphalt and one for all of the above. So no one thought that concrete allows rainwater to penetrate into the ground. Okay, a couple more here. Green roofs get their name from the color of vegetation. Is this true or false? Okay, that may have been a hard one. Most said false, but there were a few truths too, so that'll be an interesting answer. Okay. The most important factor when implementing green stormwater infrastructure is maintenance, cost, aesthetics, existing infrastructure, or your goals. What's the most important? Okay, the top answer was your goals. That's the most important factor when implementing green stormwater infrastructure. We'll see if that's true. Okay, last one is the advantages of green infrastructure include reduced stormwater runoff, improved water quality, increased community resiliency, improved livability, or all of the above. Okay, it was unanimous. Everyone said all of the above. So all of those things are what we think are the advantages of green infrastructure. That seems pretty positive. Okay, so we are going to stop the polling. And Don, I'm going to give the remote to you.
Thank you, Caroline.
Okay, there we go.
Still waiting for the presentation to come up, is that correct?
Okay. Let me see here.
Oh, because we're using the common presentation slides on your end.
Yep. Let me see here. There we go.
Perfect.
Okay, there we go.
All right, thank you. Let's see, and you've given me control already?
Yes. Yep. Go ahead and test it out. Oh, there we go. I'm sorry. I had to reshare it for you.
It appears to be working. Excellent. Okay. Well, welcome everybody. As Caroline and I mentioned, I've been a professor of practice at Lawrence Technological University for over 20 years at this point. Originally a professor, now a professor of practice. So I'm very used to engaging my audience and reading their faces to understand the speed at which to go. Unfortunately, I don't have that option today. So I'm going to do the best I can to get the speed right. And if you have questions, there will be opportunities, I think, later on to answer those. So, we jump back out. Caroline, can you put us back in there? I'm just hitting the arrow key. So Caroline, I think I see your cursor for you going over and around on the screen or not?
Yep, I'm just gonna give you control again and then I'll be done. Yep. You might want to mute. I think you can mute me. That was what I was trying to do.
Okay. What's not happening right now is it's not.
Oh, there you go. Okay, you should have control. There we go.
Right,
perfect.
All right, sorry for that, everybody.
Looks good.
What I'm going to talk about today then is I'm going to start off by actually doing Hydrology 101. I think it's very important to get a quick understanding of rainfall and rainfall patterns to truly understand green stormwater infrastructure. I'm going to then introduce green stormwater infrastructure with a lot of pictures and very, very few equations. And then some example green stormwater infrastructure techniques before turning it over to Erik and Claire to go into more detail. Okay, so let's start with the hydrologic cycle. So what I know about the hydrologic cycle is that this is covered in middle school and elementary school for part of the state standard curriculum. So everybody is seeing the hydrologic cycle in their life, some form or another. But most people, by the time they get to college and or adulthood, have kind of forgotten what the hydrologic cycle is. What I'd like to kind of focus on is bringing it down to the site level. So a lot of times with the hydrologic cycle, you see pictures that show clouds and there's some comment about we're using the same water that the dinosaurs used, but I'm going to really focus in on a site. And so when you have a natural site, which is the upper left-hand corner, typically what you have is very little surface runoff. You might get 5, 10%, maybe 20%, but limited surface water. The plants evapotranspire or breathe the moisture back up into the air, almost half of it. And the rest then infiltrates, with 25% kind of being in the shallow infiltration zone and 25% in the deep infiltration zone. The more and more impervious surface, or the more building we do, the greater that runoff gets. And the bottom right-hand corner shows 55% runoff, but that number can be as high as 80 or 90% with almost no infiltration, depending upon how much pavement and things you put over the landscape. So stormwater management, right? So the stormwater management is really just a function of three things: the rain, the soil, and the land cover, right? So the rain, the soil, and the land cover. So when we talk about rain, right? So rain is great, right? There's a lot of value to rain. It's naturally filtered by the atmosphere, so it doesn't have as many dissolved solids. It's really great for watering your garden. It's already soft. A lot of us spend a lot of money on water softening systems, but there's no calcium, there's no magnesium in rain. It's a natural fertilizer. It actually picks up atmospheric deposition of sulfur and nitrogen. So rain is a natural fertilizer as opposed to the fertilizers you have to add when you're using potable water for your watering needs. Very low salt content. We already know it has no chlorine. And really it's free, right? We have an abundance of rain in the Great Lakes state, so sometimes too much, but what we do get is free. So one of the things I want to talk about really quickly is that precipitation increases are on the rise. And I don't want to say it's a joke, but one of the things that's happened over the last several years is that my job has actually gotten a lot easier. A lot of people, they didn't believe in climate change, or You know, they may not have thought there was going to be a lot of issues with flooding. The lake levels were low. And what we've seen here over the last couple of decades is obviously water tables are going up, inland lake levels are going up, the Great Lakes are going up, the amount of precipitation we have in the Great Lakes Basin is going up. And so now people are starting to listen more. People are paying attention to green stormwater infrastructure. They're paying attention to Mother Nature. So it's made my job a little bit easier to actually discuss why this is important, because people are just kind of experiencing it. So by now you've had an opportunity to already look at the slide. And what this is really saying is that the annual average precipitation is going up. And while you have between 15% average, across, which is almost 5 inches of rain around Michigan, in reality where the majority of the rainfall increase we're seeing is actually a lot of it's happening in the fall, right? We're getting about 24%, almost 25% more rainfall happening in the fall. So that's just what we've observed, right? We're seeing water levels going up. So then the question is, well, what do we expect to have happen? And this is where you're starting to get some divergence, right? So this is precipitation increases that are predicted. And what they're really showing is on the left hand is observed change in daily rainfall amounts, right? And so you can we just talked about that. But the upper right hand picture here is to projected change in daily precipitation, extreme precipitation events. And so you're looking at all the climate models that are out there are basically saying there's going to be an increase of 10 to 20% in extreme precipitation events over the next 20 years in the Great Lakes region. So we're going to, not only have we been experiencing more intense rainfalls, we're predicted to continuing to have more intense rainfalls over the next 20 years. Oh, this got cut off a little bit here as part of the formatting, unfortunately. But what this is really showing is when we talk about rainfall distribution patterns, I'm going to look at the large circle here. Basically, 75 or 76% of all rainfall events are less than 1 inch, right? 96% of all rainfall events are less than 2 inches. And then when you get up to like 99% of all rainfall events are less than 3 inches. So if we can figure out a way to capture and treat 2 inches of rain, we're really capturing 95% of all the rainfall events that come out of the sky. And that's really the takeaway from this slide. The other takeaway from this slide is that a lot of times engineers will talk about like a 10-year storm event or a 5-year storm event or a 100-year storm event. In the case of the Midland floods, it was a 500-year storm event. What they're really talking about is an average or statistics. And they're saying that we should be getting roughly, let's say if we look at this table down here at the bottom, the part that's not cut off, we should be getting about 3.1 inches of rain once in a 24-hour period, in a 1-day period, once every 10 years. So that's what they mean by these 10-year storm events. Once every 10 years, we should be getting about 3.1 inches of storm rain in 1992. By 2016, it's gone up to 3.2. And as that continues to go, what used to occur once every 25 years is now occurring once every 10 years. And what used to occur once every 10 years is now occurring closer to every 5 years as we're moving into the future. So it's just another way of looking at how frequently these larger events happen. All right, so let's talk about the soil. I'm going to go a little faster now. So basically soil, we have hydrologists look at 4 different types of soil groups, right? And soil group A is basically sandy soils. They drain really good. And then B is kind of silty loam, C is a clay loam, and then D is clay. So and clay is going to infiltrate less than 0.1 inches per hour, and A is going to infiltrate at greater than 2 inches per hour. So A soils, sandy, got a lot of, potentially a lot of gravel in it the water can go through. B and C soils have some layers, and then D soils are the tight clay. And I'm going to leave this up just for a minute because I wanted to point something out on the right-hand side. So while both of these pictures are of clay, tight black clay soils, if you look on the right-hand side, you can actually see some fractures or some fissions in the soil. Those are from the root structures. So even if you have clay soils, if you've got good native plants with deep root structures, you can provide opportunities for water to flow through even tight soils. All right, let me cover. So this is the metropolitan, kind of the metropolitan ideas here, right? So this chart here is looking at what happens when you get 2 inches of rain and how is the soil and the rainfall going to change, right? So what this is trying to tell you is that if I have sandy soils or type A soils, if I've got a park or a meadow, I'm going to get pretty much no runoff from a 2-inch rainfall. If I pave that over with asphalt, I'm going to get about 1.8 inches of rainfall runoff from that 2 inches, or about 90%. Okay? And then when you get to that tight clay soils, you know, the parks or the meadows, you might get 0.5, 0.6 inches of rain, or 0.5 or 0.6 inches of rainfall running off, the rest of it infiltrating or evapotranspirating if your parks. And then paved surfaces, it's the same amount. So if you cover all the soil up, the same amount's going to run off. But as you're kind of mixing development, that's when the soil is going to play a different role. All right, so urbanization. So historically in Michigan, depending upon where you are, was a mixture of patchwork prairies and meadows. And then as you headed farther north, you know, white pine, deciduous trees in places. But we spent a good deal of time paving over that surface. And now we have flooding, we have water quality issues and things, you know, like even like dam failures that we saw in the Midland area when you have too much rainfall than a watershed can handle. So that brings us to the first quiz question answer, right? What inhibits infiltration, right? So what keeps it from going in? A and B, impervious surfaces, and then as we were looking at the soil, if I compact that soil and don't allow for that root structure to go into the ground, you're going to have more runoff. So A and B was the correct answer. Applying salt to a roadway, if you have too much salt, what happens with the salt, right, is it actually will dissolve in the water and then it'll actually move into the groundwater table. So it won't necessarily inhibit infiltration, but excess salt can make its way into both shallow and eventually deeper groundwater systems. So impervious cover, all of these things represent impervious cover: sidewalks, driveways, buildings, parking, roads, right? All of this adds up. And what you find out is that if you have 5 to 10% of impervious cover on a watershed, you're already starting to see a little bit of degradation. By the time you get to 30% impervious cover, you're going to see failing infrastructure, significant slump failure of stream beds and banks degradation. If you've got a watershed that's greater than 65% impervious cover, you might as well just pave it in concrete because you've got so much erosion happening. It's beyond natural at that point. Which brings us to question number 2. The best way to protect the stability of a stream channel is to, actually, I like a little offset, but it's supposed to say mimic natural hydrology. So what I always say about stormwater management is that if the watershed itself does not realize you've been building on it, that's the gold standard of stormwater management. So rivers and streams have taken their shape and their form based on natural hydrology. The best way to protect that is to mimic the natural hydrology. If we don't provide any water to the stream at all, it's going to dry up. If we provide too much water to the stream, it's going to erode and degrade. So in addition to erosion, there's a lot of pollutants in urban runoff, right? Sediments, nutrients, pesticides, heavy metals like arsenic, lead, zinc, hydrocarbons, oils, gasoline, grease, fat. All of these things are present in stormwater runoff. And collectively, we call these non-point source pollution. So excess sediments can do things like clog spawning beds of habitat for trout. Excess nutrients can cause green algae and algae blooms. Pollutants from vehicles include oil and brake dust. These things can kill the lowest levels of the food chain. Bacteria and pathogens are things like the geese, right, and dog poop. You know, it's amazing how many people I see in urban areas that just take their dog poop and just drop it right into a stormwater catch basin. So all of these things can cause bacteria and pathogen issues. So now let's get into what all of you came here for, which is the green stormwater infrastructure. So I've given you kind of a background of Hydrology 101 and why it's important to manage stormwater. Now I'm going to give you okay, how do we manage that using green stormwater infrastructure? So I'm going to start by defining green infrastructure. So green infrastructure, it says right here, according to the United States Environmental Protection Agency, I'm just going to use their definition, refers to the patchwork of natural areas that provide habitat, flood protection, clean water. At the scale of a neighborhood, green stormwater infrastructure is stormwater management systems that mimic Mother Nature. So in reality, green infrastructure and green stormwater infrastructure, while they're frequently used interchangeably, actually are slightly different things. Green infrastructure is more of the natural framework that might be at a larger area. Think about like think about flyways, think about larger prairie type scapes, and green stormwater infrastructure is what we can do at the site level, which brings us to, oh, that's a slightly different quiz question here. The green infrastructure uses plants and soil media to reduce stormwater runoff and improve quality. And the second one, which is the one we were just talking about. And that should say false, actually. The green infrastructure and green stormwater infrastructure are not the same thing. They are close, but there are some subtle differences that are important. Sometimes you also hear the word low impact development, or LID. LID is not exactly the same thing as green stormwater infrastructure, but they do still look at restoring a watershed's function. So they're frequently used interchangeably as well. All right, so what is our goal here? Our goal is try to limit the amount of impervious surface that we have and try to get development to perform a little bit like meadows, like the natural prairie scapes that used to be historically here, or the woods that used to be historically here. That's what we're going to try to do with green stormwater infrastructure. All right, so what are some of these infiltration-based techniques that we can use? Well, rain gardens or bioretention cells, planter boxes, vegetated swales and bioswales. I'm going to give examples of all of these. Street trees and tree box filters, infiltration galleries, permeable pavement. And at the end, even though these aren't infiltration based, I'm going to also talk about vegetated roofs and cisterns, because they can be really good tools in the toolbox, even though by themselves they're not infiltration based and may not mimic Mother Nature's hydrology, but they can help with the big picture. All right, so bioretention cells and rain gardens. Okay. So what's the difference? That should have been a quiz question. What is the difference between a bioretention cell and a rain garden? Again, it's one of those things that are frequently used interchangeably, but the differentiation I seem to try to make on these is that a rain garden is a landscaping feature. It's a homeowner feature. It's a park feature. So the top two would be rain gardens. Anybody can basically build a rain garden. Anybody can install a rain garden, and it can help with the overall watershed management. A bioretention cell is where you've got some sort of infrastructure in place, like a curb cut, like an under drain, like a pipe network, where that's going to require like an engineer and or a professional landscape architect to sign off on the performance. So it's being designed by and signed off on by a professional. Then we tend to call it a bioretention cell. But at the end of the day, they work similarly and do the same thing in terms of promoting evapotranspiration and infiltration. So here's some rain gardens in Ann Arbor, Michigan. Ann Arbor started a really aggressive rain garden program almost 20 years ago now. So these pictures you can see from the photo dating there are from 2007, when they put these rain gardens in front yards and side yards as part of a comprehensive program to capture downspout runoff to keep it from going to the combined sewer. Oops, it jumped on me. There we go. These are bioretention cells. So bioretention cells, you can see there's edge drains or slot drains that capture water coming off of the driveways and then divert it into long bioswales or large scale overflow basins. There's pre-treatment associated with these. So these curb cuts, fine sediments and debris and trash end up in these curb cuts, and then they flow into the cells. I'm not sure you can see my arrow or not, but if you can, these trench drains, water comes down along the trench drain, captures it. There's erosion protection control at the beginning, and then this whole cell fills up. This large graded structure in the bottom left-hand corner, that's the overflow structure. So if too much water gets in here, it overflows into that. Planter boxes. So planter boxes are effectively rain gardens or bioretention cells that have sidewalls, and they can be above grade or below grade. So this planter box on the left here has concrete walls on all sides, and you can actually see these tiny little curb cuts underneath the edge. That's how the water gets in there. So it sheet flows off the concrete and goes down into this planter box. The planter box on the right-hand side, this is on a school. So you could say, yeah, that's not going to capture a lot of water, but in a lot of situations, every little bit counts. So they took the downspout off the school, they put it in this planter box, this completely saturates and fills up with water, and then slowly infiltrates into the ground before overflowing and spilling. Both of these are examples of what we would call monocultures. So we're not going to spend a lot of time today talking about landscaping, but a big component of this is what do you want it to look like and what kind of landscaping do you want to have? So these are both single plant species, right? So you don't have, sometimes that can be easier for maintenance. If your goal is infiltration or if your goal is capture and you want to keep the aesthetics to potentially a minimum, you might just pick one species of plant and use that. And so these are more performance-based, not necessarily aesthetics-based green infrastructure. So planter boxes, they can be open on the bottom. So these are some schematics. So on the left-hand side, you've got a planter box that's open to the soil. So water will flow through the bioretention soil at the top, which is what filters the pollutants and provides the nutrients that the plants need. It'll go through a gravel storage bed. The gravel storage bed holds additional water, and then it'll slowly get into the ground. When it fills up, it'll spill over and then into an overflow pipe. A flow-through planter is one where there's a bottom on it. You know, perhaps it is up against the adjacent building, so you don't always want water to flow into the building or into like an old basement. So in this case, you've got a lot of storage inside the planter box itself, but no infiltration into the ground. There'll be an underdrain or perforated pipe underdrain. So here's two examples of that. So the one on the left-hand side, this is from Royal Oak, Michigan. That one is open on the bottom. So you've got a below grade or at grade planter box that's open at the bottom that's allowing infiltration. The one on the right is Munson Hospital in Traverse City. That's an above ground planter box. And in this particular case, this has got a solid bottom. So this is a cast, basically a precast element they delivered on site and then just directed stormwater into. So street trees and tree box filters. So a tree box filter or a stormwater tree is not the same thing as a street tree. So a street tree is a wonderful, it can be aesthetically pleasing, it can provide shade, it provides clean oxygen. There's a lot of things that street trees do well. What street trees tend not to do is be designed to take on additional stormwater, right? They're either have like, especially if you look at this tree planting program on the left-hand side in Detroit, there's no additional stormwater that's getting into this, right? It's just whatever it intercepts, whatever falls out of the sky. These, a little bit of stormwater might come in, but it's really not designed to have a lot of stormwater. A tree box filter is one where the stormwater actually goes into a catch basin or a cut and fills up where these trees are first before going into a system below it. I'll show you a picture of that in a second. So these are tree box filters where these are stormwater trees. So they're capturing more than just the water that falls onto them. As an example here, the water kind of flows down the gutter. This little catch basin here is where a lot of the sediment, debris settles out for easier maintenance. Then the excess flows past, gets diverted in here. This fills up with water, and then the tree takes it and evapotranspirates it up. What this looks like from below ground would be something like this. Water comes down the gutter, goes in a curb cut, fills this up, goes through the filtering material. Once this is full, it spills over into a storm drain underneath it. And these tree box filters are, we successfully implemented these a couple years ago in Northport, on the north, over on Grand Traverse Bay. So, quiz question time. Designing with green infrastructure always results in standing water. I'm going to guess my arrow or my circle is not going to perfectly line up. Yeah, got a slightly offset there, but that is correct. The answer is false. So you can design rain gardens and planters to have standing water, but they don't have to have standing water. There's plenty of situations where it'll drain either rapidly enough or you'll set your overflow structure so you do not have to have standing water. Infiltration trenches and galleries. So what this is you might have, basically it's going to be a rock trench, and there's the pipe in here. So you might capture stormwater off of a roof or capture stormwater off of a large parking lot, and then either feed that trench or gallery through rock, and then it'll slowly infiltrate. Or you might have a small strip of pavement. This is over in Traverse City, where water just sheet flows off of the parking lot into a porous paver system right here. And then underneath that is stone storage. It then infiltrates in the ground and then kind of feeds the cedar wetland adjacent to it. So the water is going through the ground and then into the cedars as it would have naturally. If this was all permanent concrete and we just did curb cuts, then the water would sheet flow over the top. And that's not really how these cedars were receiving water historically. So this type of system can, again, mimic Mother Nature and mimic the natural hydrology. These can get as big as you want. So this is Bryant's Park in Sutton Bay, and this is Northern Michigan College in Traverse City. These are plastic space systems, so the plastic stores it, and then in between these plastic pipes or plastic archways, we have stone, and then above that would be a parking lot or a beach or whatever, whatever. Well, in this case, it's going to be parking for the beach. In this case, it was a ball field. But we did these arch systems also in several places around Grand Traverse Bay. And so these all fill up with water and then infiltrate in the ground. And then this header row across the front, either this row here, or in this case, this row here, that header row is what distributes the water evenly into all these chambers. And it's also where the trash and the grit and the oils separate themselves out. So you can clean this header row so the rest of this remains relatively pristine and infiltratable. So another way you can do this is do an infiltration trench with trees. And this is an example of a design we did again in Northport, where you basically have water coming down the road. It's captured in a catch basin, so this provides your pretreatment. It flows in through a series of stone trenches that are connected to the trees. So the stone trenches allow infiltration into the sand. The stone trenches and the trees themselves capture water and allow for evapotranspiration and shade. And people that are just walking on the sidewalk in downtown Northport don't even realize they're walking over these underground storage chambers. Permeable pavement. So for permeable pavement, there's several different options. One option is permeable asphalt. And in this case, you can see this is traditional asphalt in the bottom left-hand corner. Water sheet flows off of the traditional asphalt onto the porous asphalt and is infiltrating. Here, the drive lane is non-permeable or traditional asphalt. And sheet flows over into the permeable asphalt, which is in the parking stalls on the edge. So, and then this whole parking lot's permeable asphalt up here. And this one's in Farmington Hills. And I can attest from this site visit, this was a day that was below freezing. It was in mid-20s, but it was sunny out. And what happens with the permeable asphalt, a lot of people say, well, this, how does that work in the winter? How does that work in the winter? So I'm not going to go through a ton of detail, but I'll give you a couple of pointers. It does work in the winter. What happens is you get a little bit of, because it's black surface, you get just a little bit of that heating effect during the day, even with a limited amount of sunshine. You can get a situation where that asphalt will warm up just enough to melt the stormwater and let it go through. And then the other thing is what happens with traditional asphalt or traditional concrete, it's not meant to have any water inside. So if you have any cracks or any space, when that water does freeze, it expands and breaks it apart and causes all the potholes we see in Michigan. With permeable asphalt or porous concrete, the void space that's in there, you can almost think of it as like the consistency of like a Rice Krispie treat. The water has room to expand. So the water that is in the pavement itself can freeze and expand, and then when it thaws, it then infiltrates. So you actually have some pretty good durability in terms of the freeze-thaw action associated with permeable pavements. Clogging is another issue. So the answer is green infrastructure does not work in cold climates. That's false, right? It absolutely does work in cold climates. You just have to have additional design considerations associated. Another example is porous concrete. Here's a porous concrete driveway. Here's a porous concrete parking lot at Hope College in Holland, Michigan. The left-hand side where the cars are, that's porous concrete. The right-hand side where there are no cars, that's traditional concrete. And so water flows from the traditional side into the porous side and then infiltrates on the left-hand side. Here's a couple concrete paver block. This is a paver block patio. And then this is a pave drain behind a store that might get covered later in this presentation. But this is a very large paver drain. And so what's happening off of the storefront here is water is flowing from the roofs through these roof scuppers. So this is actually a rainfall event here. And so the rainfall comes off of the roof, falls onto the pavement, and then the pavement basically takes all that water up. There's a stone reservoir underneath here, in addition to the water that's kind of falling out of the sky. It fills out that stone reservoir before heading down gradient. And then this porous paver patio is at Lawrence Tech. It's receiving water from some of the building and area around it as well. There's different concrete block pavers available to you. So, sorry, it jumped on me again. Well, the first two here are more somewhat decorative looking. They may be a little industrial looking, but somewhat decorative. You can also have very poured in place concrete block pavers that you can be either filled with chipstone or grass. This one here, you can't quite see it from this angle, but in between these teeth here are the openings that water can go through. So water goes through all these openings. So this type of system here, this is the loading dock at Hope College in Holland, Michigan. And so you can see that people can park their cars on there. People can put their, they can back their trucks up on here for loading and unloading at a warehouse facility in Holland. What do you have with underdrain? What happens with porous pavement? There's a couple different ways. If you have good sandy soils, you might have infiltration, so that water basically infiltrates into the ground. Eventually, if it's more water flowing onto the pavers than the ground can handle, there might be a perforated pipe underdrain that takes that water and delivers it into a catch basin or a more traditional sewer. If it fills up even farther, it'll sheet flow over the top and spill into the catch basin before falling out. So we have to size these porous pavement reservoirs to the level of stormwater we are trying to capture and treat. Okay, and if you, a full infiltration example, basically if you have really good soils, you may not have an underdrain at all, and then all the water just infiltrates. And if it ever gets a situation where it's fully saturated, it'll sheet flow over the top and into the catch basin downstream. All right, so this hard surface allows rainwater to penetrate into the ground. The answer for that one is concrete pavers. So permeable asphalt or porous concrete will allow water to penetrate, but traditional asphalt, traditional concrete do not, but concrete pavers do. So vegetated roofs and walls. So we're moving on from the infiltration techniques into some of the other techniques that are available. So there are two types of vegetative roofs, two categories of vegetative roofs. One's called extensive and one's called intensive. An extensive vegetative roof is a roof that has a very fine or small soil medium layer, and it's really meant for stormwater management as well as heating and cooling effect. So stormwater vegetative roofs are fantastic for energy benefits, thermal heating and benefits. Intensive roofs have a thick soil structure and much larger plants, a lot higher weight, and might also be in a situation where they might have additional human use patterns. So as examples of that, this would be an extensive roof, right? You can see here that there's trees on it. There's a lot of heavy duty architecture up here, even though this is providing stormwater management. It's very expensive. And then this is an example of an extensive roof. So you have intense on top, extensive on the bottom. Here, this is all just for stormwater management. There's no accessibility by the public. No one's using it. It's purely for stormwater management on top of a parking garage. Vegetation, a lot of the vegetation we use in the Midwest is sedums, and sedums can have various colors. They can be yellow, they can be green, they can be purple. So this is a vegetative roof in Port Huron, Michigan. This is a vegetated roof in Chicago, Illinois. So you can have a variety of colors associated with these sedums. You can use native grasses. If you get into more desert climates, you can do different desert type plants. So there's a lot of different plants that are available to you as part of your plant palette. And which brings us to the next quiz question, which is, I love how these keep coming up 50-50, but in reality, the answer is false. They do not get their name from the color of the vegetation. The green roofs were green when it was associated with eco-friendly or sustainable. So the green roof refers to it being sustainable, not the color. I like to use vegetated roofs because people get confused and they think they see a green roof, and they think, well, why isn't it green? Why is it purple? Why is it yellow? Well, because it can be any color you want it to be. Live walls or living walls. This is basically a little bit like a green roof or a vegetated roof turned on its side. There's a lot of potential here. So as an example, what happens here, this is a live wall in Grand Rapids. So basically these are a series of little tray systems, and these tray systems have plants in it. You can harvest the water off of the roof and then basically feed it through a drip irrigation system through this live wall system. This one here, this is this live wall, these are trellises, and this is basically a planter bed. So here the stormwater is going into this planter bed and then being fed up through this trellis system. So this is a parking structure. So you've got a green roof on top, and then you've got the live wall on the side. So all of these can take some pretty significant watering because they're suspended to the harsh elements. So these take a lot of watering, but if you are harvesting the stormwater, the rainwater, you can use that to water them. So rain barrel cisterns and water harvesting. So this can be as simple as a rain barrel. Okay, so you see a lot of these for kind of homeowner opportunities. The one on the right there is in Traverse City. The one on the left is also in Michigan. I can't remember where now. Or they could be a lot larger cisterns, right? So these are a couple cisterns in the Detroit area that are harvesting roof water, and then they're taking that water and they're taking it back inside the building for the flushing of toilets. So water reuse and circulation. So this is the 12,000 gallon cistern at Lawrence Technological University. This is actually outside the building envelope. So we harvest rainwater off the roofs, we put it into the cistern, we filter it, and then we take it back into the tub and center to flush the toilets. This is at Fairlane. So these are being used for outside landscape and irrigation. So a very large mall is harvesting that water and putting it into here. These would be drained in the winter and not used. So this is for external outdoor water harvesting and use. This is being used year round. So even though we get snow melt, as the snow melts and fills this tank up in the winter, or if we get a winter storm, that's more of a rainfall storm, we are still using it for the inside the building, which is why we bury this 4 foot underground so that it doesn't freeze in the winter. Native landscaping and riparian buffers. So this is just really the idea of using native plants. Native plants have been adapted over time to survive and thrive in this climate. So after initial establishment, they do great without watering, right? You don't need to water them as much. They've got those deep root systems that really break up hard soils. So native landscaping can be can be very attractive. It can provide habitat for pollinators. God knows we need an agrarian state like ours. We need as many pollinators as we can get to help out with our land horticulture and farming. So there's a lot of reasons to use native landscaping in addition to stormwater management. So here's an example of some turf grass conversion. So at this particular park in Southeast Michigan, the entire park was grass, and that grass was basically flowing over. Everything just kind of flowed into this pond. There was geese everywhere, so they had tons of geese. They had lots of goose poop. They had fertilizer coming off, and this pond was disgusting. And they decided, what can we do with this? Well, we recommended they convert a good portion of it, about 2/3 of it, to native prairie grass. The other third is still there to be accessed by people for fishing. And so this was the year we planted it. This is 1 year later, and this is 2 years later. And so a lot of native plants, the water quality is better, the fishing is improved, and everybody's kind of happier with the appearance of this pond. And the advantage of the taller species is you don't have anywhere near the number of geese that you used to have, because they don't like the native shorelines and the tall plants. So what is the most important factor when implementing green stormwater infrastructure, right? And the answer is actually your goals. That's kind of slid up a little bit on the formatting, but you really want to talk about what are your goals, right? So you might want to think about what does my stormwater runoff look like? And what is the water quality of it? Can I manage the water close to the source, or does it have to go far away? Is there an opportunity to dual use the water? Can I capture the water in a cistern and then use it to flush the toilet so that I'm not using potable water? Or can I capture that water and use it for irrigation? What are the infrastructure or site requirements I have? How expensive is this going to be? What does my maintenance force look like? Am I using volunteers or gardeners who have the ability to do maintenance? What do I aesthetically want this to look like? Is aesthetics really important to me because I'm in a downtown streetscape environment? Is habitat important to me? Do I want this to be like a native prairie for butterflies and hummingbirds and bees? All right, and then what's happening next door? One person's native flower bed is another person's noxious weed. So you got to be careful about land use as well. So all of these things are going to go into your decision-making process. And a lot of times what we find then is we really want a treatment train approach, right? So the treatment train approach is, okay, maybe I have water that falls on a green roof first and filters it. From there, it might move down into at-grade stormwater management, so either permeable pavers or porous pavers or below-ground treatment. And from there, it might flow into like a cedar wetland or a stormwater wetland. So you can actually have multiple ways of capturing and treating that water as it slowly makes its way through a system. And final quiz question, I believe. What are some of the advantages of green infrastructure? It's supposed to say all of the above. It got shifted on me a little bit. It's been shown to reduce stormwater runoff, obviously. It's been shown to improve water quality. Having green stormwater infrastructure promotes community resiliency. It brings down the heat island effect. It provides opportunity to limit flooding. And so you have an opportunity to limit flooding, associate even localized flooding. And then it's also been shown to improve livability. So the answer is all of the above. And with that, my portion of the talk was supposed to go to 2:30. So I believe I've got about 5 minutes left for questions. Colin, are we going to take those? I apologize. Are people entering questions as we go, or are we going to go through all the presentations first?
We do have a little bit of time for questions. So yep, I can take those now. And let me, let's see. If anyone has a question, you can either raise your hand or put it in the chat box. I don't see anything in the chat box.
Thank you, Lisa.
But we do have a question coming in here. Well, while Lisa writes her question down, a question I'm curious about is, how do you calculate how much some of these things cost? Like, you know, like what's the, is there like an estimation tool out there, or can you give us some ballpark numbers for some of these things?
That's a great question. There are a variety of estimation tools that are out there. The US EPA has some estimation tools available. We've recently just finished up a green stormwater infrastructure research project through Michigan's Sea Grant that had some information on funding. I can send that to you, and then you can distribute it to participants as well.
Yeah, that would be great.
Yeah, in reality, the best way to do this is to do construction cost estimates, you know, so like try to use local numbers for it. Rain gardens, bioswales, any treatment of the stormwater at the surface is going to be the cheapest, and it's going to be on the order of $1 or $2 per gallon managed. Green roofs are going to be the most expensive, but the value of a green roof is that not just does it manage stormwater, in reality it gives you a tremendous amount of energy savings. So vegetated roofs or green roofs tend to pay for themselves in about probably about 20 years in energy savings. And if you look at the life cycle cost, a vegetated roof is actually half the cost of a traditional roof when you look at life cycle cost over 60 years. So people have a tendency to look at construction costs, and if you look at the life cycle cost, things are a lot different. Okay, so one of the questions was, is there state funding for green infrastructure? The answer to that is actually yes. The state of Michigan has non-point source pollutant funding, which is called the 319 funds. And the 319 fund is a grant application. There's also a variety of grants that are administered by state agencies that are basically funneling money through the US EPA, for example, the Great Lakes Restoration Initiative money. Municipalities are also eligible to get funding through the state revolving fund, which is really a low interest loan program to do infrastructure improvements. What is the permitting for green roofs? Often people worry about weight load on the roof. So permitting for green roofs is basically going to be a structural permit. So it's the same kind of construction permitting you would have for building any building. As far as the weight load on a roof, you know, a brand new construction, you would basically, typical green roof is going to be anywhere from 8 to 20 pounds per square foot. And so you basically design your structural steel and your underlayment to account for that additional weight. If you're doing a retrofit, you have to look at when your building was built and have a structural engineer take a look at that. A lot of the schools I've worked with that were built like in the 70s and 80s, they found that they had enough load capacity in their roofs that they could retrofit with a vegetated roof, but some of the older buildings in the 50s and the 60s absolutely cannot. How do you see the role of municipalities in helping individuals, organizations, maybe schools accomplish some of these elements? For example, you know of any ideas / ways schools can work with local municipal institutions? So schools and school boards, a lot of it has to do with the leadership of the schools and the school boards. I know I did a lot of work with the Alliance of Downriver Watersheds, which is an organization on the south side of Detroit. And they worked very, very closely with several school systems in Southeast Michigan to basically install and implement green stormwater infrastructure. So a lot of times what I see is I see local watershed organizations like Tip of the Mitt engage with school districts that have perhaps are willing partners and then they kind of loop the local municipality. And so it's a three-way partnership that I've seen work at a variety of places across the state of Michigan. I know the Watershed Council for Grand Traverse Bay, that's worked out very well. They've worked with schools and municipalities for that as well.
Yeah, and just to add to that, the Watershed Council in Petoskey is working with Northern Michigan Community College in Petoskey, and we've worked with them before. There's a couple projects going on over there, but one of the most recent ones is a bioswale. And so I don't recall who approached who first, but our local community college, they want to be an example for kind of progressive infrastructure that's good for water quality and the environment. So I agree with Don. It can be about the leadership. They're interested in that, so they become a lot easier to work with because we're both interested in the same goals. So I think that's a good comment. Okay, any other questions? I don't see anything else in the chat. There's one more on the Q&A, Don, from Tom. It says, Sheboygan has predominantly clay soils. Is it more costly to work in clay soils?
Sorry, I muted myself. I took a drink of water. Okay. So the answer to that is it depends. Obviously, if you're looking at things like rainwater harvesting or tree trenches, it doesn't matter if it's clay soils or not, right? But in the infiltration-based design techniques, the answer is, yeah, it tends to cost more. And because if you have really tight clay soils, you're going to need an underdrain. If you have good sandy soils, you won't need an underdrain. If you have tight clay soils, you probably need a larger reservoir. So it does tend to be a little more costly to work in clay soils. The exact amount more debatable, but we've done a lot of clay soil site implementation in Southeast Michigan. So it's very feasible. It's not impossible. You just have to kind of have a little bit additional underground infrastructure. Maybe it's a 10 or 20% increase in cost associated with having that additional underground infrastructure. The other thing, I forgot what I was going to say about the clay soils. Oh, that's the other thing, is I also hear a lot of, well, our area is just clay soils. A lot of times you can find small seams of sand. So one of the things about green infrastructure is if you can search out and look for small thin layers of sand or slightly more porous or permeable soils and get water directed to those. So you may have like a 1 foot layer of really tight clay. And we're working on a project right now where we did some borehole testing, and yeah, there was like a foot of just really tight clay. And then beneath that, there was kind of a silty loam and a sandy silt. And so once we got through some of that clay, we were able to infiltrate water. So you can also look for opportunities in the stratums of soil. Okay, and with that, I think it's time for, I think it's 2:30.
Yep, I think we're gonna move on to Erik's presentation. Thanks so much, Don. That was a great overview, really great examples.
Thank you for having me.
Okay, so Erik, I am going to mute myself and then give you the remote control, and you'll just have to accept.
Okay. Okay, I think I've got the screen now. Go back to the slideshow. Okay. Well, thanks very much for having me. It's my pleasure to talk about how we've been implementing green infrastructure at Meijer. Thanks, Don, for laying out all the potential techniques and elements of green infrastructure and the kind of the theory, the advantages. And I'll talk about how we've implemented some of this work at Meijer. So what I'll first do is give you a bit of a background on sustainability at Meijer. Then I will go into a new process that we've implemented to evaluate green infrastructure at new store builds. Finally, I'll go into how we've implemented green infrastructure at several new stores. And then I'll finish talking about a parking lot retrofit study that we did in Ohio and A new project that will be starting soon on a larger full-scale parking lot retrofit. So sustainability at Meijer is really based on our purpose to enrich lives in the communities that we serve. And sustainability has been a part of our DNA at Meijer. Here's a picture of Fred Meijer, who led the company during an explosive period of growth. And he said that he wanted to leave the world in a little better shape than when he entered it. And that statement has been the foundation of environmental programs at Meijer, and is now translated into our environmental commitment signed off by our president and CEO. So our environmental commitment really starts with compliance, but now moves beyond that, from managing risk to creating value for the business and for our customers. We have a series of environmental commitments related to sustainability. The first is to offer local and sustainable products. The second is to reduce our carbon intensity as well as our overall carbon emissions. We're also committed to reducing plastics by improving our packaging and promoting the use of reusable bags. When it comes to food waste, we have set a target of reducing food waste by 75% by 2025. And finally, we're committed to growing responsibly, which includes advancing green infrastructure. A little note on this picture, we're a Great Lakes-based retailer, and managing stormwater and improving our communities by installing green infrastructure, again, is a key element of our purpose-based sustainability. All right, what I want to do is give you a little bit of background on how we evaluate green infrastructure when we develop new stores. So this process, from the time we identify a property until the time a store opens is about 5 years. So early in that store development process, during our due diligence phase, we're evaluating the suitability of a site for green stormwater infrastructure. And the reason for that is that when we go in for municipal approvals, we have to have the stormwater management systems already identified and come up with some preliminary designs. So early in that due diligence process, we want to see whether sites are suitable for green infrastructure. So we've got a multi-step flowchart that we use to conduct that evaluation. So the first question we ask is what types of soils are present on the site? And Don rolled through the different types of soils and their impacts on green infrastructure. So clearly if we have sands, perhaps some sandy loams, those are very favorable for implementing green infrastructure. As we get into other silts and silty loams, it's possible. We may have to make some adjustments, but when we do get into clay soils, again, they'll require an under drain or some other engineering change. The second question that we look at is what's the local seasonal high groundwater elevation? Clearly, if we've got groundwater depths greater than 6 feet, then we can infiltrate stormwater without any issue. If we're between 3 and 6 feet, again, we may have to make some adjustments in the design. It's still possible. If we're in a very shallow groundwater situation where the groundwater is present at less than 3 feet below ground surface, then green infrastructure will be pretty tough to implement. The next question is really, next few questions are on the regulatory end. If the site is located in a combined sewer overflow area or an area that's under a US EPA consent decree that may mandate green infrastructure, then typically that would be a yes for us on this flow chart. And what comes to mind is Cleveland. We have moved into the Cleveland market last year, and so being able to implement green infrastructure was important for us to demonstrate and to understand as we moved into areas that required green infrastructure as part of site development. Fourth question, do local regulations restrict the use of GI in site development? This is fairly rare, but if they do, then it's typically a no. Next question, do local regulations specify that green infrastructure be required or incentivized as part of site development? And And in many municipalities now, sites have to meet often 90% of the pre-development hydrology of a site. So there we would be incorporating green infrastructure into that design. The local regulations specify a range of hydrologic design conditions, such as groundwater recharge volume, required infiltration, or so on. Again, if it's part of the regulatory framework, then we'll be moving into green infrastructure. Are there any other special conditions that might prohibit the use of GI? And here, we're often looking at brownfield sites, for example. We do build on brownfield sites, but if we've got underlying contamination beneath the site, then we would not be infiltrating stormwater as part of that site development design. And are there other special conditions that might promote the use of GI? A bit of a catch-all question. So we go through this process then we're in the due diligence phase early on in the development of site to decide whether we're going to move forward with additional design, geotechnical evaluations, and deeper technical decision-making on the suitability of green infrastructure. So what I'll do now is go into the stormwater, the green infrastructure designs at several of our stores. And the first that I'm going to discuss is our store in Manistee, Michigan. The Manistee River is probably one of the prized trout fishing rivers that we have in the state. And this site sits adjacent to wetlands that discharge to the Manistee River. So ecologically a very sensitive site. And so we had to design some very robust stormwater systems to make sure that we did not have any kind of negative impacts from stormwater onto that habitat. So if we look at this overall site plan, what you will see is kind of standard impervious asphalt here is just in gray. And we have catch basins located in that parking lot that have 2-foot deep sumps to collect sediment. And stormwater from these areas, from the impervious surface, then pass through a stormwater treatment chamber, a swirl chamber, where again, sediment can settle in the bottom of that chamber. We can also collect any floatables, plastics, and so on. This store also has porous asphalt in purple. So you'll see that here. When to discharge stormwater from, and in that porous asphalt, of course, we're infiltrating directly into the sandy soils below. But in these other impervious areas, after water passes through the Vortec swirl chamber, it is then discharged to an infiltration area, these areas in green here on the south end of the store. And that treated stormwater can then infiltrate there if it's a fairly small rain event. If it's a larger rain event, the stormwater can run over the edge of that infiltration basin into these level spreaders, which again slow down the water velocity, mitigate any potential erosion, and the stormwater can discharge into this wetland on the south side of the store, where it again is discharged into the Manistee River. So the slide here in the upper right shows that permeable asphalt. I think Don showed a picture in his presentation of someone pouring a bucket of water into the permeable asphalt. We've got similar pictures when we first rolled out that system. And then here is the level spreader in the back of the store, just the beginning of the infiltration bed. The level spreaders further out there. So this system has worked very well. It's been in place. We're going into year 4. We conduct routine sweeping of these porous asphalt areas. We instruct our snow removal people, again, not to pile any snow in these areas. We have had a bit of clogging in this infiltration area and something that we're going to take a look at this summer. But overall, the sediment collection has gone well. The vortex swirl chamber, again, hasn't had to be emptied yet. We've had plenty of capacity in the sump. So we will go into a 4-year maintenance cycle this year, and we're going to empty out all the catch basins in the swirl chamber. But otherwise, the system has performed quite well. The next store is a store we opened recently in Warren. And this is a store that Don helped design. So this is our Meijer footprint in this pink area. The rainwater and melted snow and so on from the rooftop discharges to these pavers behind the store. The picture that Don showed you earlier, here's just a little different angle of those pavers that run behind the store. Stormwater that hits the impervious surface here is actually directed to permeable pavers that we have in these dark green blocks. And then we also have a bioswale at the front of the store for additional discharge from that site. So this is what these pavers look like. Again, we go into a twice yearly sweeping of these pavers to make sure that they keep running well. But again, the store, we're through year 2 and the systems have worked quite well. One thing I do want to mention, the driver behind installing green infrastructure at this store was some very serious flooding that Warren had faced several years previous. This store was formerly a nursing home medical center. It did have stormwater detention available. But in order to perhaps mitigate any future flooding, we wanted to be part of the solution. And so we installed green infrastructure at this store to support those efforts in the community. Okay, next I'm going to move into a research study where we wanted to take a look at the impact of green infrastructure elements in a parking lot retrofit. So this is store 212 in Reynoldsburg, Ohio. This is an area that has been experiencing severe flooding and erosion associated with just the overall development in the 10 acres around Dysart Run, which is a creek running close to the store. So we were interested in determining, how effective perhaps a parking lot retrofit could be. And so what we did was we installed these permeable pavers near this area of the store and a bioretention cell over here. We monitored stormwater discharge for a full year to develop a baseline, and then after these systems were constructed, continued to monitor for another 20 months to look at the performance of those elements. The good news here was that the bioretention cell performed very well, knocking down stormwater runoff by about 80%. In the permeable pavers, however, that element did not perform as well for a couple of reasons. One problem we had were some preferential flow paths running through this permeable paver section. The loading was higher than expected. This was not a pristine, finely graded parking lot. It had seen its better days, and so some of those preferential flow paths played havoc on the system. We also had some issues with clogging. We had the snow removal team found a nice place to put all their snow, and I don't know why the permeable pavers were such a great target. So we had some management issues around that system, but overall the systems performed well. Certainly bioretention did quite well. So a few lessons learned. Bioretention was a very simple practice to operate and maintain. We went to the site twice a year to basically clean out any collected sediment, do some pruning of the vegetation, renew some of the mulch. One opportunity for improvement was just to make sure that we would get trash out of that area more frequently. And one other gap that we had here was we should have established signage around that area just to inform customers and store team members of this green infrastructure cell, because we had landscapers that wanted to tear out the weeds, and you know, they considered the plantings not particularly appealing. And then when it came to the permeable pavement, like I said, we had some preferential flow paths that that impacted the performance. The loading was much too high, and we had maintenance issues. So here are some pictures of what those pavers looked like when they were clogged, and then clogged after a season of snow storage. You can see they're in pretty bad shape, but then we went in with a regenerative sweeper, pulled those materials out. So, you know, it's important to note, I think one of the take-home messages here is that, you know, green infrastructure is not maintenance free. You know, these systems have to be maintained to operate as designed. So establishing expectations and educating the users of those systems and those maintaining those systems is absolutely critical to getting these systems operating as designed. So I'm going to finish talking about a recent project award. Don mentioned the 319 grant program through Eagle, and we just received confirmation of this parking lot retrofit up at Store 33 in Traverse City. And in this store, it runs adjacent to Kids Creek, which is a protected stream. And we are going to be implementing bioretention in this part of the store parking lot, underground infiltration in this area, and porous pavers here to, again, reduce the amount of runoff, stormwater runoff, as shown by these existing yellow pipes and discharge outlets. So we're really excited to begin this project. Kids Creek, protected stream, discharging eventually to Grand Traverse Bay. Again, ecologically very sensitive areas, and doing our part to be able to mitigate the impacts of stormwater runoff. Okay, that's my last slide. Certainly opportunity to take questions with respect to GI at Meijer. Oh, before I end, we had a little lag in the slide deck. I did want to acknowledge the work done by Don's team at Lawrence Tech and Ryan Winston at Ohio State on the parking lot retrofit study. They did a terrific job and gave us a lot of lessons learned as we roll out these parking lot retrofits on a larger scale. Thanks. Open for questions now.
Okay, we've got about 10 minutes for questions. Just checking the chat. Okay, if there are no questions for Erik,
I'll throw one out there that I would ask myself.
Okay.
And I think, you know, one of the questions is around cost. And of course, you know, we're under pressure to reduce our new store construction cost. At that new store build in Warren, that cost us about an extra $100,000 to implement green infrastructure. So, you know, ultimately, we always hope that we can install green structure and reduce some of the redundant gray infrastructure. But I think some of our municipal partners are still a ways away from allowing for those sorts of design modifications. So it is definitely an uptick in cost for us to implement green infrastructure. But when there are cases like Manistee and Warren, where there are clearly significant benefits where we have to implement green infrastructure, it's a great thing for us to do.
Yeah, I think that's great, Eric. And I would guess, I think you usually need approvals from the city or some municipality. Does including green infrastructure make it easier to kind of get through those regulatory processes?
Well, in Manistee, it was absolutely required because of the sensitive environment we were building the store. And in Warren, I'd agree it also did facilitate approvals because of the flooding issues they had experienced not long beforehand.
Okay. So we did have a question come in on the Q&A screen, and it says, the vacuuming of pervious pavements is sometimes seen as a barrier to installation. Are all pervious pavements needing vacuuming twice a year?
Well, that, and Don can
Yeah,
drop
Don, feel free to weigh in.
as well. But I think, we have found that if we, that Reynoldsburg example is a good one where clearly we had to do the vacuum sweeping, and it's been beneficial at our other sites as well. I don't really see it as a barrier. I think going in, we just have to understand that these systems are not maintenance free. You can't plant a rain garden and leave it alone. You can't install permeable paving and leave it alone. They require maintenance just like everything else.
So yeah, I'll chime in very, very briefly on this one. So not all of them need vacuuming twice per year. It really depends upon the loading ratio, which Eric talked about, like how much drainage area you have, how much sediment is going to be in that, how many leaves are going to be in that. I mean, there are some porous concrete parking lots and pavement in Grand Rapids that went years without vacuuming and we're still performing. You don't typically want to leave things alone for years and not vacuuming, but it's possible that you could go several years in between vacuuming. It really has more to do with the use and how's the water getting on there and how much sediment is that carrying. In some areas, you might actually need to vacuum it quarterly, like 4 times a year. So it's highly variable, unfortunately. And it's really more about how the people that are installing it, the people that are designing it, basically need to put together a maintenance plan that gives you an idea. Is it going to be every year, every other year, 4 times a year? So it is going to vary.
It's definitely an empirical exercise. I mean, we do visual observations, but we can't oftentimes measure unless we look for ponding out in the asphalt after a rain event or something like that. But it's like Don said, there's some obvious impacts, and you just have to observe and determine what the required frequency will be.
And I mean, compared to conventional infrastructure, would you say that green infrastructure is more of it's a frequent maintenance, but maybe it costs less as opposed to the conventional infrastructure, which might cost more just on a more infrequent schedule, like basically eventual replacement?
I think that's a fair representation. I mean, kind of typical stormwater infrastructure, again, has to be maintained, but perhaps not as frequently and not as, but when those repairs do come in there, they could be more robust and more costly.
Okay, so it's almost 3 o'clock. So thanks, Eric. I think that was a really good perspective from the private sector that we don't normally see. So that was very interesting. So we're gonna go on to Claire next. Let me see if I can get this pulled up. I think there's a lag here. Oh, there we go. Okay, Claire, I'm going to mute myself and then I'm going to give you remote control.
Okay, thank you very much, Caroline. And thanks everybody for attending today's webinar. I'm going to bring home with the municipal case study and hope that the folks in Sheboygan can maybe find some similarities between your situation there at the northern tip of Lake Huron and this particular case study which is at the southern tip of Lake Huron. So my name is Claire Schwartz. I've been with Fishbeck doing stormwater management for about 30 years now. So I've seen a lot of transitions, and I've been involved in stormwater infrastructure for many of those years in its infancy and now through its development. So this is a municipal case study, and see if I do have control of the screen here. Okay, yep, this is a municipal case study for the St. Clair County Drain Commissioner. So that'd be Bob Wiley, and we were a teaming partner with BMJ Engineers and Surveyors. The name of it's Forest Manor Drain Project. It's a county drain, and it was done as a green infrastructure project for the Forest Manor subdivisions. So here's a location map. As you can see, the location is on Lake Huron, just north of Port Huron and south of Lexington in Fort Gratiot Township. So zooming in a little closer, we actually had two subdivisions encompassing about 24 acres of land located between M25 and Lake Huron. And there was an open water course to south called the Galbraith Drain. And you can see in red there, orange, the existing storm sewer system that served the Lake Meijer and the Forest subdivisions. Also unique to these subdivisions were the fact there were two private parks at the end of the road just prior to the Lake Huron beach. We made use of those for our stormwater infrastructure. Here's a picture photograph of the two parks that we ended up putting best management practices on. So a little bit of an introduction to the subdivisions, and to give you the setting here. There are former cottage communities that progressed over the years in permanent homes, but little consideration had been given to stormwater management. And that's being indicative of the photos here. You can see the settling streets. You can tell that water had ponded there. There was the storm sewer tile system, as I showed previously, but again, it was in aging, in disrepair, and you can see the location of some of the inlets not necessarily appropriately placed. And so there was also high groundwater, and people were experiencing crawl space wetness. So some additional photographs showing how conversion to permanent homes really increased the imperviousness of the area. So I'm thinking back to Don's slides that he started us out with that showed the effects on stormwater runoff from increases in impervious. Taking a quick look at some of the soils of the area, we didn't have clay soils necessarily. We had some much fine sands over the majority of the subdivision. So there was infiltration, but then it was also accompanied by high groundwater as well that were poorly drained. So from the soil borings, the clay was at a deeper level, and essentially the wetland sands over the stiff blue clay is kind of indicative here in Michigan with the high water table. So the drain itself had been in place for years, probably the 20s or 30s. And here you can just see a picture of it. There was a west arm and an east arm, consists of clay tile, relatively small size tile, about a mile of pipe, and then with the outlet down to the south there at the Galbraith Drain. Oh, and then backing up a second, I wanted to show you as well that we had places where a lot of tile crossed private properties, parcels, and then there was some areas of the subdivisions that weren't served at all by the drainage system. And then this is just a picture to give you a little better sense for the Galbraith Drain, the open channel then that outlets to Lake Huron. And there you can see the Forest Manor 18-inch pipe coming to the Galbraith where it flowed through about half a dozen very large homes, very nice homes there on Lake Huron, with driveway crossings and stabilization measures to keep the channel from eroding already. So here's some photos of what that looked like. There's the outlet of the Forest Manor drain. There's a typical channel in front of the homes, then the outlet into Lake Huron. So the issues I already touched upon, flooding was the primary driver for the petition to do a drain improvement project. So this was from a 1-inch drain, which shouldn't cause this much problem, but it did with the existing drainage system, particularly for this house. So yeah, we talked about the poor drainage, the high groundwater, sump pumps running continuously, the deteriorating streets. The tile itself, we did televise it, and it was in poor condition. Usual things, someplace the cracks in the displaced joints, and someplace root intrusion. And also, interestingly enough, the photograph shown here, the elevation of this is lower than the Galbraith drain during a flood event. So during larger events, because this is connected to the Galbraith, water can back right up and flood this to an even greater extent. So they had that complicating factor to deal with as well. So under a traditional design, you know, you might think, well, you'd do is you'd upsize the pipes and, you know, discharge to the Galbraith. These days, that's not acceptable because of downstream impacts. We have to consider flooding, channel stability, and water quality. So you probably need to purchase some land, do a large detention basin before you released to Galbraith drain, or maybe you do a direct discharge to Lake Huron. So that would be, you know, what you'd think of as a traditional design approach. And those were options that we're all looked at as well. But in the end, we went to property owners with a design plan. And first and foremost was to improve public health and safety. And that was really the impetus of the petition. But we went in to introduce the homeowners who ended up paying for a majority of the project. As you'll see, we wanted to introduce them to green stormwater infrastructure techniques. So the first probably year of the project was meeting with property owners, talking through the suite BMPs, educating them, lots of meetings and interaction. And as we went through everything, and in this particular project, it was interesting that some techniques were just not accepted. So while you can see some green boulevards there between the sidewalk and streets, the idea of putting a bioswale or rain gardens in those areas was just not something that appealed to the people as part of the this public infrastructure project. They like their grass, they like their lawn, that's their culture, and so that did not end up being a BMP that was used. We had talked about stormwater reuse for irrigation, and the township was not at all happy with that in terms of the fact that, for the fact that they do provide water to this area, and so that would kind of go against what they wanted to achieve. And then pervious asphalt pavement wasn't really viewed as an option for them, so they were a little bit leery about the texture of that for the streets in general. So in the end, came up with primarily 2 of the BMPs that you heard Don and Erik talk about earlier. So instead of paving entire streets with permeable asphalt, we decided to use brick pavers in some of the key low areas, the drainage collection areas of the streets, and then pave with traditional asphalt, which gave them the smoother surface, the more traditional feel that they were to maintain on their roads for the rest of the areas. Then in the parks, we made use of those for underground infiltration chambers so that above the park could totally be used in the same manner that it was used prior to the project. We did construct a new outfall to Lake Huron, but the outfall was not a primary outfall, it was more of an overflow outfall, so that as the infiltration beds filled up or we didn't get infiltration through the paver systems or a larger storm occurred, then the outfall would engage. The southern portion of the system, we left in place a tile. You can see the much larger lots in the southern portion of the area here. So we left the tile in place and cleaned it, and that continued to discharge the Galbraith, but with a lot less contributing area. So that improved things in the downstream area there too. So with the new design, we were able to expand the drain to serve some of the neglected areas of the subdivisions, maximizing the benefit of green infrastructure in a way that was palatable to the property owners, try to minimize the cost by just doing it in key areas and not everywhere, and then minimize the impacts to the beach with the overflow. So some of the challenges we had were that, as you saw, some of the drain was located outside of the private road, so we had houses over the drain. In those cases, we left the old drain in place and just connected it up. But the new drain is all located within private right-of-way. Sandwiched between all the existing utilities, so finding a place for it was important. And then working within the narrow right-of-way. Also, we were subject here to fluctuating Great Lake levels, being so close to Lake Huron. So this is kind of a definitive slide that shows you how the system worked. So the paved drain pavers, shown here, allow stormwater that falls on that, rainwater, infiltrate to the stone bed below the pavers. Then catch basins located in the curb are there to catch runoff that's coming from the asphalt areas, as well as kind of a belt suspenders for the pavers. We get runoff from those. Catch basins then go into perforated drain tiles connected to the main storm sewer. The main storm sewer is also perforated and receives flow from the tiles and what infiltrates through the paved drains. So this functioned in two ways. If we had in a high groundwater situation, as shown here, then perforations in the storm sewer tended to lower the groundwater and have an influence on it in that way. So that provided relief for those crawl spaces that were getting wet. In a low groundwater situation down here, then the whole system acted to infiltrate that stormwater and reduce the runoff and associated pollutants directly into either a Great Lake or a surface water body of the state. I've included this slide for those interested to see the actual design cross-section is used for the paved drain section. So you can see we use 10 inches of an aggregate crushed 6A stone underneath the paved drains with axial biaxial geogrid, and then some gravel beneath that. Okay, so moving on to the treatment system. This is one of the parks, and this is our infiltration bed. So again, using the underground chambers, and we also had the had some reservation ports and the isolation chamber layer put into this as well. So the good news was the groundwater dropped off towards Lake Huron. So we were able to have enough vertical distance to route our stormwater to the infiltration chamber and allow for some filtration before discharge to the lake. We had good sand in this area because it was beach sand. It protected the beach, overflow only when the chamber is full. we're protecting the Galbraith by disconnection, and vice versa, the forest manor drain system was protected from the floodplain of the Galbraith in a backwater situation. Again, I've included typical cross section from the drawings of the chamber. Again, infiltration chambers in stone. And here you can see where the water's collected from the subdivision right to a diversion chamber where primary flows are going into our infiltration bed. There's our isolation row and our inspection ports. What that would overflow, then we discharge to our Lake Huron outfall. So construction. The project was completed in 2016 at a cost of $2.4 million. So what did they get for that? They got 1 mile of new underdrained roadway, including storm sewer and structures, the infiltration chambers, and the outfall, including water and sanitary adjustments that were necessary. So I did a little, in preparation for the presentation, I went back and looked at the bid and did a little comparison cost to see that with the pavers in the areas that we used them, they cost probably about $88,000 more than traditional hot mix asphalt over an aggregate base. So that was about an $88,000 add to make sure we had the paved drains. The infiltration chambers and 2 parks totaled $61,000. So that would not have been done in a conventional system. So adding that up, I was at about $150,000 more than traditional for the green infrastructure. But however, from that, you'd have to subtract the cost of probably purchase of land for a detention basin and construction of a detention basin. So overall, majority of the cost here, I think, was for the, just for the pipe itself and for the paving of the roads. But the green infrastructure really didn't cost that much more when you're looking at the 2.4 million. So funding, we got a USDA Rural Development loan, which helped spread the cost over 20 years. MDOT kicked in for special benefits because of the water quality features that were included, and that the fact that some water from M25 drained into the system. They helped pay for this above what they'd have normally paid for in just a normal special assessment. But the majority of this project was paid for by special assessment, which included the township and the property owners. Finally, we did receive a SAW grant that primarily paid for the design engineering on this, and then we needed to provide a state report, final report on the water quality benefits. So a few construction pictures. You can just see how that the chambers were installed. There's the outfall going in to Lake Huron with special end treatment. And again, a very dynamic environment. So finally, the results. Property owners, I think, were very pleased in the end. Value for their money. They got new streets. You see, just looks like a whole different neighborhood. Improved aesthetics. Property values increased. They did get the groundwater control, improved drainage, and reduced flooding. We're also protecting water quality with minimal impacts to the beach. So I'll just go through the next couple of slides showing you some of those results. So here's a before and an after of the forest subdivision. And this is what the pavers look like. So you can see just smaller areas of pavement, but very attractive. A little bit of belt suspenders. Here's the catch basins and the curb lines. And then there's the lake down there. But big improvement over what they had before. In terms of groundwater, We had installed some piezometers, and before the project, groundwater was running up here, 585s, you can see. Then project construction begins in 2016. And for as long as we were monitoring here through 2017, we dropped the groundwater by about two feet or so, pretty consistent. So pretty dramatic, and that was positive benefit for the homeowners. And then I threw in this profile of the drains. Here's the Lake Huron outlet. Here's a typical profile of the storm sewer in the aqua color, top of the pipe. The hydraulic grade lines for our design storm. So you can see some pressure flow up here. And then here, this dashed line is the groundwater. That was when we started the project. So you can see that hovering on the 585 mark there, and then lowering it down, and here how it drops off towards Lake Huron. And the outfall pipe down here. So historic high levels by the red line, just underneath our infiltration bed. So again, during low levels, plenty of room for infiltration. Currently, we're within 6 inches of the bottom of the bed. So I'd expect that now during cyclically high lake levels, we're going to get more frequent overflows. However, it's still functioning to provide some infiltration, because our outfall is definitely not discharging fall storms. And then here's the low area in the subdivision that when we were connected to the Albright drain, water could back right up and just fill that up to the 100-year, to the elevation of the Galbraith. So give you a sense for what was happening there. And then finally, from a water quality perspective, we reduced runoff by about 30%. Reducing runoff equals a reduction in pollutant loads. And this was the EPA stormwater calculator that we needed to run and submit with our SAW grant to Eagle. Looking at the effects of water levels of Lake Huron, our outfall. This was when after the outfall went in April 2017, and then December of 2018. Still quite camouflage there on the beach, so not a very obtrusive outfall at all, especially compared to the Galbraith sheet piling. And then this picture was just taken in March of 2020. So what you can't even see the pipe. The drain commissioner does go down and clean it out occasionally, but water still discharges through the stone. You can see the trail here where it had discharged for some bigger storms, in the past, and not that long ago. So everything is working, even with the cyclically high levels. So I just also, in preparation for the presentation, asked the drain commissioner, so what kind of maintenance have you had to do on the project since it was installed in 2016? And so their records showed that 2017, they did some vacuuming of the pavers, cost them about $8,000 for cleaning. And then in 2018, they had another $4,500 expense related to some settling of the pavers. And then nothing in 2019, but then $3,000 for cleaning the paver areas again. So for this project, it looks like maybe on average cleaning once a year. But overall, the system is performing well, and homeowner feedback has been overall very positive on the project. So it's been in place for 4 years now. So that's all I have, and hopefully that gives encouragement to the folks up in Sheboygan that you can do similar things and get some similar results. Thank you.
All right, thanks to our presenters. Wow, that was a lot of information. So now we have some time for some questions. I don't see any quite yet, remember you can raise your hand or use the chat box. There's a couple things while we're waiting for the questions to come in. Just a reminder that this is the first of 4 workshops, so the workshops will slowly converge more and more on Sheboygan, ultimately with a demonstration project. And our next workshop will actually be another online webinar on August 13th, so I can share information about that. I will be sending out a link to the recording when it's ready. Don also said that he would share something from Michigan Sea Grant about construction costs, so I can add that. And then also we are offering the continuing education credits, so there's an opportunity to get a certificate for those as well. So our presenters shared a lot of good overall information and then a lot of good specific information that I think we could definitely see in Sheboygan. So are there any questions? I have a question, I think probably mostly for Claire. In that specific example, were those drainage pathways, were those designated drains, county drains? In northern Michigan, it's actually pretty common for counties to not have any designated drains. And so I'm wondering if having that designation can help move some of this stuff along.
Yeah, Caroline. So yes, they were established as county drains. And so they had associated with them a drainage district that was, redelineated now as they had the petition for the project so that we could more accurately determine who's served by drains. But it does give you a funding mechanism and an entity that's responsible for maintenance as well. So I've seen the drain code used as a really good tool and a mechanism for these types of projects. So yeah, I would encourage exploring that type of a partnership and seeing if establishment of a drain, particularly when you have a lot of different property ownership and a lot of different interests, it can be the way to go if you don't have a municipal system. Something that's maybe entirely located within the city of Sheboygan, really not a reason if you've got the municipal jurisdiction there, and the city street right of way.
I see. Okay, so that would be more for something outside the city jurisdiction.
Correct.
Okay.
But if you have a joint city township, that can bring the township in too to help pay as well.
Yeah, that's good to know.
Yeah.
Okay, well, if there's no further questions, I am going to start a feedback poll. And so we will share the results of that, and then we'll still have a little bit of time for questions. So this one you can vote for all, or you can choose multiple answers for each question. This is just to help us get feedback for future workshops and just to kind of know what are people most interested in. So the first question is, which topics or aspects of the workshop did you find most interesting or useful? Techniques, hydrology and resiliency, case studies and practical applications, planning, benefits and drawbacks, how green infrastructure works with conventional infrastructure. The second question is, what green infrastructure information would you like to learn more about? Funding mechanisms, always popular. Design, economic benefits, finding contractors, maintenance, codes and ordinances. And then finally, what do you believe are the biggest obstacles locally to implementing green infrastructure projects? Money, time, skepticism, aesthetics, lack of public support, changing the status quo, maintenance, knowledge. Oh, knowledge is on there twice. That's a very important one, and permission. All right, so with that, I am sharing the poll results just for you to check out. I'll be using that for to gauge how well this webinar went and our future efforts in Sheboygan. Thanks again to everyone who attended. Thanks to Don, Eric, and Claire for presenting. We learned some really great information. And thanks to the Great Lakes Commission and the Herb Family Foundation for funding the series of workshops and work in Sheboygan. And I think that will conclude our webinar. Thanks, everybody.